back to Physics News. I'm Damian Dubowitz, and my lab partner is Brian Aleman Hernandez. Today we're diving into one of the most visually fun experiments of the semester, projectile motion. It's the physics behind everything from basketball shots to rocket launches. And this week we got to explore what makes an object travel just right through the air. Our mission for this lab was to test how the angle of a launch changes the distance a projectile travels. We used a steel ball launcher, carbon paper targets, and good old-fashioned gravity to record our results. Before we could launch anything, we made sure our equipment was level, stable, and accurate. The launcher was set about 1 meter off the ground. That gave us a consistent starting height for every shot. We launched the same steel ball at 4 different angles: flat, 30 degrees, 45 degrees, and 60 degrees. Each launch left a tiny mark on carbon paper where it landed, giving us a simple way to measure how far it flew. We started with a flat, horizontal launch to figure out one key piece of the puzzle: the muzzle velocity, or how fast the ball leaves the launcher. Basically, by measuring how long the ball takes to fall from the launcher's height to the ground, we can calculate how fast it was moving forward. When we ran the numbers, we found that our launcher was shooting the ball at roughly 3 meters per second, a solid, consistent speed for every shot. Once we knew the speed, we started changing the angles. Each angle affects how the ball splits its energy. Part of the speed pushes it forward, and part of it lifts it up. At smaller angles like 30 degrees, the ball stays lower and flies farther. At steeper angles like 60 degrees, it goes higher but lands closer. And somewhere in between, usually around 45 degrees, you get the sweet spot, where height and distance balance perfectly. We ran each angle 3 times and took the averages to get reliable results. The differences weren't huge, but they told a clear story. The lower launches tended to go a little farther, while the higher ones spent more time in the air but came down sooner. Even without showing all the decimals, we can explain the math behind what happened. Every launch has 2 motions happening at once: a horizontal motion that stays steady, and a vertical motion that's pulled down by gravity. Combine the two and you get the perfect curved path, the parabola, we all recognize from physics class. By applying the same equations we used earlier, we compared what the math predicted to what we actually measured, and surprisingly, our data lined up pretty well. Using those velocity components, we calculated theoretical ranges. For our 60-degree angle, our theoretical range in meters was 1.23, the measured range was 1.27, and the percentage error was 3%, as opposed to our 30-degree angle, which our theoretical range was 1.34 meters, the measured range was 1.80 meters, and the percent error was 34%. The biggest difference came at the lower angles, where the ball rolled a bit after landing, and that made the distance slightly longer than predicted. Even so, our percentage errors dropped dramatically at the higher angles, meaning our results were getting closer to perfect as we improved consistency. What we really learned is that projectile motion is incredibly predictable. It's one of the first places in physics where the math and the experiment match almost perfectly. No matter how big or small the object is, if you know the launch speed, the angle, and the pull of gravity, you can predict where it'll land. That's the same principle used in sports, engineering, and even rocket science. And while we weren't launching any rockets in the lab, the idea is the same. It's all about understanding motion in two dimensions. So, what did we take away from Lab 6? First, that 45 degrees really is the golden angle for distance. Second, small errors like uneven launch angles or tiny air currents can make noticeable differences in the data. And finally, this lab showed us that understanding the math helps explain what our eyes see in motion every day. It's the perfect example of how concepts on paper turn into motion in the real world. This wraps up our Lab 6 report on projectile motion. A big thanks to everyone who helped with the measurements and calculations. And remember, in physics, it's not just about getting the numbers right, it's about understanding why they work. For Physics News, I'm Damien Dubowitz. Thank you for watching, and we'll see you next time in the lab.